Well, we're privileged tonight to have a speaker from Bozeman. Dr. Charles Kankelborg is going to give us a talk on light. And Charles is an associate professor of physics at Montana State in Bozeman, our sister campus, right? Charles conducts scientific research on the atmosphere of the sun. By the way, let me ask a question. What's the closest star to the Earth? The sun. Very good. You didn't fall for that trap. Very good. Charles also likes to develop instruments that get flown into space to study ultraviolet light radiated by the sun. So that's some pretty exciting research that he's doing with that. Some little background information. Charles is you were born and raised in Tacoma, is that right? So he's a Washingtonian. He graduated from the University of Puget Sound in 1989 with a bachelor's degree in physics. And then he went to Stanford University and got a PhD in physics in 1996. And then joined the faculty at MSU Bozeman in 2001. Dr. Kankelborg has taught a broad range of undergraduate and graduate courses. He's won several teaching awards. He's received the Presidential Early Career Award in 2008, which is a pretty prestigious award. And the Charles and Nora Wiley Award for Emeritus Research in 2010. He's served extensively on NASA review panels and is a principal investigator of a rocket research program and is a co-investigator of the NASA IRIS satellite mission that was launched in June of 2013, so last June. So after Charles' talk, there's going to be a raffle for some science prizes. So don't just take off after his talk, but so at this point, let's welcome Dr. Kankelborg.
Oh, well, it was a beautiful drive over here today. It was a sunny afternoon driving over. Is the volume okay? Okay. I haven't used a mic in a long time. Usually my classes are smaller than this, so. The picture on the screen is a picture of my father, and I'd like to dedicate this talk to him because I learned so many neat things from him. I've been interested in light ever since I was a little kid, and that's the subject of this talk. But my dad taught me things, just all kinds of things. Like, he taught me how to sharpen a drill bit. Does anybody here know how to do that just with a bench grinder? Okay, maybe one person, two people, all right, there's a few of us, three people, all right, great. There are a few of us who know how to do this. It's a little bit tricky, but there's pictures here that show you how to do it. I asked Dad a lot of questions, and he, more often than I could believe, had really interesting answers. Part of it was that he was a machinist, and he knew how to do stuff, and he knew about machines, he knew about cars, and all kinds of cool stuff like that. He had also been a pilot, and so he knew about aviation. But there was a question I remember asking him that really sort of left him stumped. I asked him, what is light? And he didn't have a whole lot to say. And I thought, wow, there's a question that Dad doesn't really know the answer to. Maybe I could try and figure that out. So that kind of, I guess in a way, got me interested in light. And although my dad didn't have a physics kind of answer for what is light, he did encourage me to play with optics. So the family binoculars, for example, were a favorite thing of mine. And I think I spent many hours staring at stars through the binoculars before I realized that they weren't focused. And I thought that these big blurry blobs that I was looking at were like, I thought I was like seeing a big, thing out there in the sky. So those are some of my fond memories. My dad also, being a machinist and working in the shipyards in Tacoma, growing up, he used to bring things home off of the ships every once in a while because they would essentially junk ships. They would strip them and salvage them, and sometimes he brought home optical instruments that were gun sights from naval destroyers and things like that. So I'd take those apart, and there would be prisms and lenses. And by the time I was in high school, I had built telescopes, really bad telescopes, but they were telescopes and they worked, and other things like that. So, what do we know about light? What's familiar to us? Well, I think we all have kind of the intuition that light goes in straight lines. So you see a scene like this. This is a picture that my wife took when we were on a cruise, and you can see these rays coming out of the clouds, and they point back to where the sun is located. So evidently light likes to travel in straight lines. And another manifestation of that is shadows. You can't see my shadow up here on the stage, but I can. And you've all had the experience of, you know, walking down the street with the sun at your back and seeing this perfect, you know, perfect cutout of yourself on the pavement in front of you. And that's because light goes in straight lines. So that's one thing that's true about light. We call those rays. Another thing is color. And color is, I think, kind of a mysterious thing, at least when you first think about it. I mean, you know, I have a red ribbon on, and I see a red coat out there in the audience, and I see all these other colors, greens and blues, and so we tend to think of those colors as belonging to the things that they're attached to, like the ribbon is red. But the thing that may not be quite so obvious is that, well, it's just that the ribbon is reflecting red light and not other colors of light, and so it's the red light coming into my eye that to me identifies this as a red ribbon. So color is not just a property of material things that you can touch and feel, it's a property of the light itself. This is a picture, by the way, taken by Joe Shaw. He's an electrical engineering professor at our university, and he loves taking pictures of rainbows. This is a particularly beautiful one. And you see there, the colors, they're a little bit hard to see from way back, but red and orange and yellow and green and blue there in the rainbow, just different colors of light. Well, rainbows have intrigued people for a very long time, and they contain within them kind of a lot of the keys to understanding what light is. Isaac Newton, who was kind of a famous guy, wrote a book called Optics. And this is the first page of the first edition. You can see that he had a little spelling problem. Well, okay, they actually just spelled things different back in those days, but I like to say that. And I think it says MDCCIV. Anybody know what year that is? They don't teach Roman numerals anymore, do they? I think if I'm reading it right, that's 1704 is the date of this first edition. So that's a long time ago, right? If you think about dates that you know in history, 1776 is a good one, right? So this is before our Constitution, before we had a United States or had even thought about it. Isaac Newton was figuring out this stuff about light. And he figured out that white light, actually, the kind of light that's shining on me here, and I'm almost kind of blinding me, making it hard to see you all, is light that contains all of the colors. And for a long time, people knew about something called refraction, that is, when light enters some transparent substance like glass or water, it gets bent as soon as it crosses that boundary. And I have a little picture of that here. This is water, or this is a droplet of water and light, white light coming in and getting bent and getting reflected actually at this inside surface, and then getting bent again as it comes back out. It turns out at these two bendings here and here, the light starts to separate out into colors, and Newton was the first person to realize that was really the basis of the rainbow. Actually, he may not have been quite the first person to realize that, but he took this a little bit farther, and he had a neat experiment with a prism. And he used that prism, which is just an angled piece of glass, to spread out the light into a rainbow. And then he did something that nobody else had thought of before. He took another prism and he shined his rainbow on that prism. And the second prism was turned the opposite way, so it would bend the light back in the other direction. And what happened was that the rainbow merged back together again into white light. And so he said, that's it. White light is made out of all these different colors of light. You can split them apart and you can put them back together again and it's white light again. So that was a fantastic discovery. Newton also thought that light was made out of particles. He called them corpuscles. You've heard of corpuscles, like red and white corpuscles in your body, right? Those are particles of blood or cells of blood. Well, he thought that there was something similar to that going on in light, that it was made out of particles. And he figured the bigger particles were different color than the smaller particles or something like that. He tried to use this to explain refraction, and he got quite a ways trying to explain things on that basis. Now, the story at this point, the story of learning about light, takes an interesting turn because a fellow named Young, Thomas Young, did a very funny experiment. He had, let's see, I guess I need a little pointer here. Let's see if I can do this. Uh-oh, warning, the scientist is now walking across the stage. Okay, so Young did something really interesting. He took a screen and he cut a couple of holes in it, or a couple of slits, and he shined light on it. And so the light was going from left to right, and on the screen behind that, he might have expected to see a couple of dots, you know, which are kind of like the shadow of everything except for the holes, right? Isn't that what you would expect? You just see some light going through and see maybe a dot of light there and a dot of light there. Well, that's not what he saw. He actually saw a bright patch there, and a bright patch there, and a bright patch there, and another bright patch here, another bright patch up here, and they were kind of more or less equally spaced. And that's weird. I mean, that's really weird, because he had more bright patches than he had holes, and the bright patches were actually maybe a little bigger than the holes, so that's very mysterious. The explanation that he had for this, and actually I have to admit this was kind of a premeditated thing on Young's part. He actually thought he knew what would happen, and he was right. But he had been arguing against Newton's theory for a long time and saying, light isn't made out of particles, light is made out of waves. And so now look at this animation again. See if I can get it to play. We have the light going from left to right. Some of it gets through the holes, and the ripples spread out from the holes. And if light is indeed made out of waves, then those waves interfere with each other in a very funny way, so that you get really strong crests and troughs of wave here, let's say, and also along here, leading to that bright spot, and also along here, leading to that bright spot. So this is Young's explanation. He said, the only way light could do this is if it was made of waves. And that was brilliant. And that was what turned everything around from people making fun of Young to people starting to wonder about Newton's theory and whether or not it was right. So this was a breakthrough time. 1803 was when he did his experiment. And now I want to think about a little tiny change to this experiment. One of the properties of this light that's interesting is the distance between the crests and troughs. So there's a low point in the wave, and there's another high point, and then there's a low point as these waves are propagating along. And I could measure the distance between those, and that has a name. We call it wavelength. That wavelength is a characteristic of the wave, whether we're talking about water waves or sound waves or any other kind of waves. They all have a wavelength. Well now, what if we changed that wavelength? I've made it just a little bit shorter. Can you see that? That it's a little shorter? The waves are squished together a little bit. And I still have 3 spots of light ending up over here, but I wonder if you can see that they're a little closer together than they used to be. I'll back up. There. There's with the longer waves. Oops. Uh-oh. All right, and there's with the shorter waves. Let me try it again, because I had a little hiccup there with my computer. Longer waves, shorter waves. So you see how the spacing between these bright patches actually depends on the wavelength. The longer the wavelength, the farther apart those little patches are. And so let's actually try something with that, because now I'm curious about these waves. Since I have a handy-dandy red laser pointer, let's see what some red light does when I shine it through this little widget that I have here. This is not just a double slit like Young had. It's a fancier, more modern thing called a diffraction grating, but it's very similar. It's like Young's double slit, except it's got slit after slit after slit. It's got 100 slits per millimeter, very closely spaced. And that's actually a rather coarse one. The one that we flew on the IRIS satellite last year had 3,600 slits per millimeter. But I'm going to shine this red light through it, and let's see what happens. Okay, you saw a bright spot in the middle, right? And did you see some other spots up beyond it? Actually, what if I shine it on the ceiling? Isn't that cool? All right, now I need you to do something. Remember how far apart those are, okay? And I'm going to grab a different laser. All right, I'm going as fast as I can. Here's a different laser, a blue laser. Oh, is that different? All right, so I think that those spots from the blue laser are closer together. Would you agree? Yeah. All right. So is the wavelength of blue light shorter or longer than red light? Great. You're all physicists now. Give yourself a hand. So you have figured out what Thomas Young figured out, that different colors of light, the colors that Newton broke up into the spectrum, are actually different wavelengths of light. We've demonstrated the wave nature of light right here. And so there you go. That's all you need to know, and we know what light is, and I guess I'm done early. Isn't that how it works? Well, there's another kind of a funny thing that happens. And there's going to be a little bit of arm waving here, because this is a little harder to explain, but there's a fellow named Planck, and this is a picture of Planck up at top here as a young man, working as a scientist, trying to understand a thing called blackbody radiation. Blackbody radiation is one of those things that scientists have given a name to so that they sound like scientists. But what you know as blackbody radiation is that phenomenon where you turn on the electric burner on the stove and it starts to glow orange. You've seen that, right? Okay? Or if you were to heat it up even hotter, it would turn yellow and then white and then maybe even blue if you got it really hot. And Planck was trying to explain the colors that come out in the blackbody radiation. And it turned out that the theory of the day was all wrong. It was a theory based on the wave theory of light that said that you should get a whole lot more blue and ultraviolet light than anything else when you heated something up. And that just wasn't true. And so Planck made what he called a purely formal assumption, which is a way of saying, I have no idea why I did this. And he decided to treat the light as if it were particles. And believe it or not, that theory, assuming that the light was behaving like particles, is what gave the right answer. And that was very mysterious. Then, just 5 years later, Albert Einstein, who was busy discovering things that year. I mean, he was really busy. In 1905, he published like several different things that were all different results, all in different fields of science, all at once. He just had a huge brainstorm that year, and one of the brainstorms that he had was about a thing called the photoelectric effect. This is something you might not have experienced, but it turns out if you shine ultraviolet light on a metal surface, that metal surface gets charged up. It actually spits electrons off of the surface of the metal, leaving behind atoms that are not neutrally charged anymore. So it's a lot like rubbing a comb in your hair, and that gets charged up with electricity, right? You can do the same thing to a metal surface with ultraviolet light. The funny thing is, you can't do it with red light or green light, and that's a bit mysterious. And Einstein looked at what Planck had done and realized if he made the same assumption that Planck had. Planck's assumption was that the shorter the wavelength, the closer you get to blue, and actually blue is not where it ends. Ultraviolet is even shorter wavelength yet. I would bring an ultraviolet laser, but none of us could see it, and so it wouldn't be a good demonstration, okay? But at any rate, Einstein said, well, Planck said that the shorter the wavelength, the more energy those particles of light have. Maybe it takes a certain amount of energy to start breaking charges off of this metal plate and breaking them off of the surface. And it turned out that when he made that assumption, the photoelectric effect, suddenly all the experiments, he could explain the results. And so what that meant was this thing that Planck called a purely formal assumption, like, I have no idea why I said this. You know, it was really real. And light really was made out of particles. Now, at this point, you're thinking, what? We started out with Newton, and Newton said they were particles, and then Young came along and we said they were waves, and now we're changing our mind again. That's really weird. So, I have another little demonstration here. And let's see. I have some articles of clothing that are familiar to us in Montana, those of us who hunt. This is a bit of hunter orange that I have. I'll just hang this up right here. And I also have this scarf, which is not hunter orange. It's kind of a nice bright green. And I'm going to shine my laser pointer on it just to see what happens. So, all right. Now, everybody tell me what color the laser is when it hits the cap, all right? Red. Okay, I'm going to shine it on the green thing, and what color do you think it's going to be? Red. All right, so this laser only makes red light, and no matter what I shine it on, the light is red, okay? Now, here's my blue laser. Same kind of deal. Everything that I shine it on, it always looks blue. Oh. Oh. What happened there? Now that's weird. That's weird. Now I don't know about you, but I think that my blue, I have to wake my computer back up. It's getting a little bit sleepy. It was a long drive over here. The computer is tired, so it's going to sleep. And anyway, so I don't know about you, but I think that my blue laser, at least to my eye, doesn't look really quite as bright as the red one. It's certainly no brighter. They're not all that different. And yet, you know, when I shine the red light on these objects, they're just reflecting red light. But when I shine the blue laser here, I get the feeling that there's like more light. You see how that suddenly gets brighter? Isn't that weird? These are fluorescent articles of clothing, and what that means is they absorb light that's at a shorter wavelength and they turn it into a longer wavelength. The thing about longer wavelengths like green and orange is that our eyes actually respond better to them. We can see them better. So it's not really brighter, but it looks brighter to us. And the other thing about this is that it actually fits really well with Planck's purely formal assumption. That is that shorter wavelength light has higher energy, and therefore there are things you can do with these higher energy particles that you would never be able to do with any amount of lower energy particles, like excite this fluorescent dye and make it do this crazy thing. Okay? So this is actually a demonstration that light is made out of particles. And now, these are the same lasers that I used to show you that light was a wave. Are you confused yet? Well, we're just about at the end, because this is the part where I say that it wasn't until I got to college and learned quantum mechanics that I understood that this is completely incomprehensible. But I can solve the problems, I can do the math, I can do quantum mechanics and get an A in it, but it's still weird to me. Because the answer I was taught to the question, what is light? Is it a particle or a wave? Is yes. And that's all that I have.
I'd like to show our appreciation to Dr. Kankelborg with giving him a plaque, so I'm going to present that to him, and then after I present this, Elizabeth's going to help with the drawing. We have a bunch of prizes that we'll give away, so Elizabeth will be in charge of that. Okay, our first prize is for a radiometer. So go ahead. It's Julian from Lame Deer. This is a nice light activity kit, so that goes to
Kelsey Chandler.
electrical science kit. This probably has diffraction gratings, all kinds of stuff in here. This would be a fun one.
Kylie Jeffco.
Oh, Riley.
Right.
Okay.
Sorry.
Here's a DVD on light.
Marlena Garcia.
And here's a light experiment kit.
Brandon Howlett.
And here's a lighted microscope.
Chrislyn from Harn Middle School.
Okay, this is a pocket telescope microscope combination, so this looks pretty cool.
Maddox Ruby from Luther.
The final and grand prize. Build telescope microscopes. Whew, this looks pretty good.
Starla Redwolf.